Who's ready for some more fun with limits? In this section, we're going to look at how to evaluate the limit of a function by factoring, use the law of limits to evaluate the limit of a polynomial or rational function, and evaluate the limit of a function by factoring or by using conjugates. So as we saw earlier, we can find the limit of a function by plugging the value in, especially if it's a polynomial or a rational function. However, if for all x not equal to a, if f of x equals g of x over some open interval containing a, then the limit of f of x as x approaches a is the same as the limit of g of x as x approaches a. So think about this limit as x approaches 1 of x squared minus 1 over x minus 1. If you factor that numerator out to be x minus 1 times x plus 1, this limit then would be the same as just the function limit of g of x equals x plus 1. Everywhere, though, except at x equals 1, possibly. But we're talking about the limit of the functions would be the same. And so it's possible to factor out a function and get rid of a point that would make it undefined. But it's not really getting rid of it, so just think back to where it was. We have to still exclude that value that caused that hole in the graph. So looking at the two types of graphs, these are identical except the f of x one, that was the rational function, has the hole there at x equals 1. So in doing that, the process essentially would be factoring that out, dividing out that x minus 1 from the numerator and denominator. And we end up with limit as x approaches 1 of x plus 1. That's the equivalent limit, which is going to be 2. Now, the indeterminate form, though, by the way, we've been discussing lots of limits where we had 0 over 0. That is called the indeterminate form. And the strategy for solving something like that is this. First, we need to make sure that our function has the appropriate form and cannot be evaluated immediately upon or using the limit laws. We then need to find a function that is equal to h of x equals f of x over g of x for all x not equal to a over some interval containing a. To do this, we may need to try one or more of the following steps. If f of x and g of x are polynomials, we should factor each function and cancel out or divide out any common factors. If the numerator or denominator contains a difference involving a square root, we should try multiplying the numerator and denominator by the conjugate of the expression involving the square root. If f of x over g of x is a complex fraction, we begin by simplifying it. Then we apply the limit laws. So just recall that a squared minus b squared is a plus b times a minus b. A perfect square trinomial, that is the a plus b squared, is a squared plus 2ab plus b squared, or that factors down to be a plus b squared. If you have a sum of cubes, a cubed plus b cubed is a plus b times a squared minus ab plus b squared. And the difference of cubes, a cubed minus b cubed, is a minus b times a squared plus ab plus b squared. So you probably remember those, but I'm just going to go over those. The greatest common factor, or GCF, can be factored out of a polynomial. Checking for our greatest common factor should be the first step in any factoring problem. Trinomials with leading coefficients of 1 can be factored by finding the numbers that have a product of the third term and the sum of the second term. That's if you've seen my technique of doing that, that's the diamond problems. Trinomials can be factored using a process called factoring by grouping. Perfect square trinomials and differences of squares are special products and can be factored using equations. The sum of cubes and difference of cubes can be factored using equations. Polynomials containing fractional and negative exponents can be factored by pulling out a greatest common factor. Factoring by grouping, this is the AC technique. Hopefully you recall that. And then greatest common factor, the largest polynomial that divides evenly into the polynomial. Also recall the conjugate of a sum or difference of a rational and irrational term. So if you have a plus b root c, the conjugate is a minus b root c. So it might be helpful in doing that in the numerator or denominator, whatever is appropriate to help to simplify what you're doing. Okay, let's look at this first one, evaluating the limit by factoring and canceling. And again, canceling is just another way of saying dividing out the common factors. So this would be looking like limit as x approaches 3. In the numerator, I can factor an x out. That's x times x minus 3. And in the denominator, I see a 2x. And then I see an x as a factor. I'm betting that one of those is an x minus 3. Let's see if that's the case. That means it would be a 2x plus 1. That's my guess. 2x times x is, that's 2x squared. That's good. Negative 6x plus x, so it's negative 5x. It works out. So then we're going to divide out what is common to both, and the x minus 3s are common to both. And we end up with the limit as x approaches 3 of x over 2x plus 1. And that's going to be 3 over 2 times 3 is 6 plus 1 is 7. So 3/7. That was kind of fun, huh? Let's try another one. What can we factor out of this numerator? So this becomes the limit as x approaches negative 3. As you see right now, if I plugged in that negative 3, I'm going to have a 9 down below. 9 minus 9 is 0. Up on top, I have a 9 minus 12 plus 3 is 0. So it's a 0 of a 0 case. But the numerator would factor, to be an x plus 3 times x plus 1. And the denominator would factor to be an x plus 3 times x minus 3. And then we can divide out these x plus 3's. And what are we left with? The limit as x approaches negative 3 of x plus 1 over x minus 3. And now I can put that negative 3 in there, and that'd be negative 3 plus 1. I'm running out of space over there. Over negative 3 minus 3. So it looks like it's going to be negative 2 over negative 6, or 1/3. Cool. Now there's also a video you can watch from the publisher about doing this. So take a look at that in the text that's embedded. Let's try another problem. How can we do this one? Okay, it looks like we can factor out. So we have the limit as x approaches negative 6 of 6 times x plus 6. And then down below we have, looks like it's going to be an x minus 8 times x plus 6. So we can divide out the x plus 6's. And we end up with the limit as x approaches negative 6 of 6 over x minus 8. So that's going to be 6 over negative 14, or negative 3/7. Okay, let's do another one. Hoping that the numerator factors with an x plus 10. It looks like it does. We have the limit as x approaches 10 of x plus 10 times, that's a 10, x plus 1 over x plus 10. So that means it divides out, the x plus 10's do. And we have the limit as x approaches 10 of x plus 1, which would become 10 plus 1, which is 11. Fun stuff so far, right? Okay, let's go on. Okay, now here's an interesting one with the square root of x plus 2. So if I were to put that negative 1 in there, I'd have negative 1 plus 2 is 1, square root of 1 is 1, 1 minus 1 is 0. Down below, I'd have negative 1 plus 1 is 0. So I have the indeterminate form. So I'm going to multiply this one by the conjugate of that, which becomes the square root of x plus 2 plus 1 over the square root of x plus 2 plus 1. So Haven't changed the value. I'm multiplying by 1, and it's the conjugate. So if you just recall that an a minus b times an a plus b, and we just talked about this a few minutes ago, it's going to be a squared minus b squared. So this gives us the limit as x approaches -1 of x plus 2 minus 1 over x plus 1 times the square root of x plus 2 plus 1. And now we don't have a problem with the 0 over 0 situation, or do we? So now as we go on, at first glance, I still have an x plus 1 down below. I have the limit as x approaches -1 of x plus 1 over x plus 1 times the square root of x plus 2 plus 1. Oh, look at that. That worked out for us. The x plus 1's divide out. Now that leaves us with the limit as x approaches -1 of 1 divided by square root of x plus 2 plus 1. So now if I plug in that -1, I have 1 over, that's going to be the square root of -1 plus 2 plus 1. That's going to be 1 over 2, isn't it? Okay, let's try another one like that. So where we're going to deal with having a conjugate. And the goal is, hopefully, with that conjugate, is that you have something that's going to divide out of the numerator and gets rid of that 0 that you might encounter with the denominator. This is another example. If I put the 5 in the place of the x up on top, I'm going to have a 5 minus 1 is 4. Squared 4 is 2. 2 minus 2 is 0. Down below, 5 minus 5 is 0. So if I again multiply this by our conjugate, the square root of x minus 1 plus 2 over the square root of x minus 1 plus 2. I have the limit as x approaches 5 of, now again, this is going to be an a minus b times a plus b squared, so it's going to be the first thing squared, which is x minus 1, minus the second thing squared, which becomes a 4. And then down below I have an x minus 5 times the square root of x minus 1 plus 2. So we have x minus, no, don't forget my limit, as x approaches 5 of x minus 5 over x minus 5 times, don't run out of space here, square root of x minus 1 plus 2. So these x minus 5's divide out. So we have the limit as x approaches 5 of 1 over the square root of x minus 1 plus 2. Now if I plug in that 5, I have 1 over the square root of 5 minus 1 plus 2. It's 1 over square root of 4, which is 2, plus 2, which is 1/4. Pretty cool stuff using those conjugates. Okay, let's keep going here. Recall, given two rational expressions, add or subtract them. So factor the numerator and denominator, find the least common denominator of the expression, and then multiply the expressions by the form of one that changes the denominators to the least common denominator, add or subtract the numerators, and simplify. So they're given this example, the common denominator is xy, so we're going to multiply by y over y for the 5 over x, multiply by x over x for the 6y, and we end up with a 5y over xy plus 6x over xy, and that gives us 6x plus 5y over xy. Recall, given a complex rational expression, simplify it. So we'll combine the expressions in the numerator into a single rational expression by adding or subtracting. Combine the expressions in the denominator into a single rational expression by adding or subtracting. Rewrite as the numerator divided by the denominator. Rewrite it as multiplication and multiply. Isn't it interesting? All these skills we learned in algebra and pre-calculus are coming to be of great use now. Yes, it is. Okay, so here's an example of that. They're going to combine the numerator. So that's y over 1 plus 1 over x. You're going to multiply the y by x over x to get xy over x plus 1 over x, or xy plus 1 over x. So you have a single term on top, a single term on bottom. That means the top one's being divided by the bottom, or the top one's being multiplied by the reciprocal of the bottom. And then that's what you get. Okay, what happens here? Example, evaluating limit by simplifying a complex fraction. So let's simplify the numerator. So if that's okay if I step aside here and just look at the 1 over x plus 1 minus 1/2, look at that first. And to combine those, I need to multiply the 1 over x plus 1 by 2 over 2, and the 1 over 2 by x plus 1 over x plus 1. So that's going to give us 2 over 2 times the quantity x plus 1. Then I have minus 1 times x plus 1 over 2 times the quantity x plus 1. So we have 2 minus x minus 1 over 2 times x plus 1. So that's going to be negative x plus 1 over 2 times x plus 1. And I could see where this might be going. So we could treat this as the negative of x minus 1 over 2 times x plus 1. Okay, now I'm going to take this back and put it in place of this numerator. So I'll have the limit as x approaches 1 of negative of x minus 1 over 2 times x plus 1. All that's over x minus 1. And so this is like saying the limit as x approaches 1 of negative x minus 1, negative of x minus 1 over 2 times x plus 1 divided by x minus 1. So another step, and I get it. If you can skip that step, that's fine with me. I don't want to lose anyone, so I'm going to show this step. So limit as x approaches 1 of negative of x minus 1 over 2 times x plus 1 times 1 over x minus 1. And from here, I will divide out those x minus 1s. And this gives us the limit as x approaches 1 of negative 1 over 2 times x plus 1. And now I could plug in that 1 for the limit and see what happens. I'm going to end up with negative 1 over 2 times 1 plus 1. So it's negative 1/4. That's not so bad. Kind of a fun process there. So feel free to pause if you need more time. Okay, let's try another one like this. So again, I'm going to step aside here and look at this 1 over x plus 2 plus the 1 over 1. And really all I have to do is multiply the 1 over 1 by x plus 2 over x plus 2, because 1's already, it's already a factor of everything. So we end up with 1 over x plus 2 plus x plus 2 over x plus 2 to give us an x plus 3 over x plus 2. So now we have the limit as x goes to negative 3 of x plus 3 over x plus 2. All that's over x plus 3. And some of you might be really comfortable doing some canceling or dividing out at this point, but I'm just going to take this like I did in the last one, a couple of steps here. The limit as x approaches -3 of x plus 3 over x plus 2 times, I'll do the divide by x plus 3. So it becomes the limit as x approaches -3 of x plus 3 over x plus 2 times 1 over x plus 3. So these divide out. And we end up with the limit as x approaches -3 of 1 over x plus 2. Now we can plug that in. We get 1 over -3 plus 2, 1 over -1, which is -1. That was a cool process. Okay, feel free to pause if you need more time there. Moving on there's a video to watch in the embedded textbook if you want to go there. And let's go on to the next thing. Evaluating the limit when the limit laws do not apply. So here we have the limit as x approaches 0 of 1 over x plus 5 over x times x minus 5. So if you plugged in the 0, and you'd have 1 over 0 plus 5 over 0 times 0 minus 5. So you'd have 1 over 0 plus 5 over 0. And what we're going to need to do is combine these into one term. So let's think about this. 1 over x plus 5 over x times x minus 5. So I'm going to multiply this one by x minus 5 over x minus 5. And that's going to give us x minus 5 plus 5. I should say x minus 5 over x times x minus 5 plus 5 over x times x minus 5. We have the same denominators. We can combine the numerators. So that's going to become an x on top. We have x times x minus 5 on bottom. And then what happens? We have an x on top and an x on bottom. So those can divide out. And we're left with a 1 over x minus 5. So this becomes the limit as x approaches 0 of 1 over x minus 5. That's going to be 1 over 0 minus 5, or -1/5. That's pretty cool. Aren't you glad you learned all those rational expression rules? Okay, moving on. We have another one like this. In this case, I would factor the x squared minus 2x minus 3. So we'd have 1 over x minus 3, and this factors to be x minus 3 times x plus 1. And the common denominator is obviously going to be x minus 3 times x plus 1. So I'm going to multiply over the first term by x plus 1 over x plus 1. And we end up with x plus 1 over x plus 1 times x minus 3 minus 4 over x plus 1 times x minus 3. So that ends up being an x plus 1 minus 4 over x plus 1 times x minus 3. So that's an x minus 3 over x plus 1 times x minus 3. And look at that. That x minus 3 is in the numerator and denominator. So we end up with 1 over x plus 1. So it becomes the limit as x approaches 3 of 1 over x plus 1. So that's 1 over 3 plus 1, or 1 over 4. Okay, let's keep moving on. It's going to be a long video. It's a long section here. Evaluate each of the following limits if possible. So what if we look at this? We have the limit as x approaches 3 from the left side of the square root of x minus 3 compared to limit as x approaches 3 from the right side of the square root of x minus 3. So just looking at the graph, our square root of x minus 3 is going to be a radical, let's use the square root of x, but shift it over to the right by 3 units. So it starts at 3. Oops, doesn't look what I did there. It looks something like that. So for the first one, the limit as x approaches 3 from the left side, that one's going to be does not exist, because it doesn't exist to the left of the 3. But to the right of the 3, it does exist, and so that limit will end up being 0, because it's going to 0. Okay. So here we have a two-sided limit using the limit laws, so it's a piecewise type function. And notice that it's changing at 2, and that's what we have here. It's approaching 2 from the left, or approaching 2 from the right, and so what's the overall limit? If the limit is approaching the same thing from both directions, then we would have a limit here. If they're not approaching the same thing, it's going to be does not exist. So while this is not defined at x equals 2, we can look at our limit as x approaches 2 from the left of f of x is going to be the limit as x approaches 2 from the left of that. What's on the left side of the 2 is going to be the 4x minus 3. So 4 times 2 is 8. 8 minus 3 is 5. Now from the right, we have the limit as x approaches 2 from the right of f of x is going to be the limit as x approaches 2 from the right of the one that's on the right side, which is going to be the x minus 3 squared. Okay, so 2 minus 3 is negative 1. Negative 1 squared is 1. So we have here 5. Here we have 1. So this limit does not exist because it's not the same thing from both directions. Okay. Let's try another one of these. So now what's happening, this is an interesting function because it's looking at, we have the limit as x approaches negative 1 from the left. I'm wondering if something did not translate when I printed this out, meaning we have the other two limits because this has two show solutions. So we have from the left, so we have this one's from the left. And then this one's from the right. And so in this case, we could say, well, let's see, the limit as x approaches negative 1 from the left is going to be of f of x. It's going to be the limit as x approaches negative 1 from the left of negative x minus 2. And that means you plug a negative 1 in there. So negative and negative 1 is 1 minus 2 is negative 1. The limit as x approaches negative 1 from the right is going to be this of f of x is the limit as x approaches negative 1 from the right of x cubed. So it's going to be negative 1 cubed, which is negative 1. Look at that. They're the same. However, I mean, if we looked at f of negative 1, by this definition, it's going to be 2. Yet if we looked at the limit as x approaches negative 1 from either side of f of x, since from the left and from the right both approach negative 1, it's going to be negative 1. So again, I think something got messed up here in the translation, but probably what they're after. Okay, getting closer to the end of this one. So we now turn our attention to evaluating the limit in the form limit of f of x over g of x as x approaches a. So with the limit of f of x as x approaches a is k, and k is not 0. The limit of g of x as x approaches a is 0. Then we have something in the form k over 0. For the next one, we look at this, and if you look at that right off the bat, it looks like we're going to have a number over 0. But let's look at this the following way. The limit as x approaches 2, but treat this as x minus 3 over x times x minus 2. We could factor that x out. So we end up with the limit as x approaches 2 of x minus 3 over x times the limit as x approaches 2 of 1 over x minus 2. So in the first case, you would end up with, plugging the 2 in there, 2 minus 3 is negative 1, so negative 1 over 2 times, in the second case, you're going to end up with 1 over 2 minus 2 is 0, so 1 over 0. Now, 1 over 0 is commonly referred to as infinity. It's also undefined, but in our case, we'll call it infinity. So negative 1/2 times infinity would give me negative infinity. The textbook has a slightly different version of this. They have approaching 2 from the left. So if you approach 2 from the left, that would make this 1 over x minus 2 a negative infinity, and then that cancels to become a positive infinity. Okay, let's do this last one here then. And let's see here. Same type of thing. We have the limit as x approaches 1 of x plus 2 over x minus 1 squared. So let's see. That's going to be something like the limit as x approaches 1 of x plus 2 times the limit as x approaches 1 of 1 over x minus 1 times the limit as x approaches 1 of 1 over x minus 1. So if we break it up like that, we'd have 1 plus 2 is 3. Then we have 1 over 1 minus 0. So 1 over 0, 1 minus 1. And then 1 over 1 minus 1. So we have 3 times infinity is going to be infinity. That's it.